Okay, we're going to go ahead and get started. Hi, everyone, and welcome. My name is Colleen with HEBI Robotics, and I will be moderating today's webinar, which is titled Redefining the Robotic Arm. The presentation and demos today will be done by Andrew Willig and Hardik Singh. All participants will be muted by default, but please feel free to use the question feature on the side of the GoToWebinar sidebar, as well as the chat feature. We will be answering questions throughout to the best of our ability, but we do have a dedicated Q&A portion at the end of the webinar. And with that, go ahead and take it away, Willig.
Thanks, Colleen. Just a quick introduction. I'm Andrew Willig. I'm a mechanical engineer here at HEBI Robotics, and joining me is Hardik Singh. He's a product manager here at HEBI Robotics. Just a quick background about HEBI. It was founded back in 2014 with a bunch of engineers spun out of Carnegie Mellon. We have an office here in Pittsburgh, Pennsylvania, and also in Salzburg, Austria. HEBI's mission is to help customers do in days what could otherwise take months to do with traditional hardware. This is kind of our motto. We like to say we are accelerating the future of robotics. We also have customers that span across both the research and industrial sectors and all across the world. So what I'm going to do right now is play a video. So most of you probably saw this as kind of our marketing ploy, but I'm just going to talk over this video. So HEBI Robotics works to making building custom robotic systems easy through this agile robotics development platform. We want to change the way that robotic systems are being built and become the de facto standard for motion control, the next generation of automation. Our expertise, like I mentioned, includes robotics, both hardware and software, with a core focus on motion control. Motion control is basically, how things move. Like I mentioned, we have over 100 customers in 26 countries spread out across the world. We also work with our customers to take ideas from concept all the way through to production. The hardware, like you see in this video, is very modular. You can kind of think of it like working with Legos, and we'll get into more detail as the presentation goes on. And then we also have the software tools that are very user-friendly, and you don't need a PhD in robotics to control our robots. So as this video plays on, you'll see, it's very easy. I'm using an iPad here to control this arm that took me only, less than half an hour to put together, with standardized hardware that we'll get into more detail. And what's so great is it's very easy to adapt our tools and put them onto different kinds of things like a mobile base here and do other cool demos with it. So I'll let this video finish playing out and we'll move on. And you can see here too, I'm also using the iPad's AR kit, so the camera and IMU accelerometers gyros in the iPad to actually do motion control with the arm. And again, we'll do some demos later to show that. So just to give everyone a quick overview of what you can expect to gain from this webinar, we're going to start off. We want to redefine something, so we need to give it an initial definition. So we're going to start off and look at what a robotic arm looks like in today's world. Next, we're going to show you how HEBI Robotics is changing that definition. Then we'll take a quick look at some customers using HEBI Arms, both in the research lab, but also out in the field. And then finally, we'll dive into some of the software demonstrations that I alluded to in the video with HEBI's ARM API that ties everything together that we talked about. One thing to note here for new and current customers, this ARM API is the latest innovation in streamlining our software workflow. So what we want someone either watching this live right now, or if you're watching this as the recording, use this as a tool and watch it again and again and again, and use it to help you as a resource to further accelerate your robotics development. Again, if you want a more generic view about HEBI Robotics as a company, or as a more overview about our platform, you can go back and look at our prior webinars online. Now I'm going to pass it off to Hardik to define robotic arms.
Hi, everyone. Thanks, Willig, for passing it back off to me. I am going to take some time today to talk about how we define the robotic arm and challenge why we need to change that definition as we move into the modern day. Let's first ask the question, what is a robotic arm? And as we always do, the first thing is to check on the internet. So what does the internet say? The internet says that a robotic arm is a mechanism connected by joints, allowing either rotational motion or translational displacement. The important thing here to note here is that it talks about the links of the manipulator can be considered to form a kinematic chain. And this touches upon a key change in our perspective about the robotic arm. The robotic arm isn't anymore just a large machine that you pick up, place, and set to a task, as you might see in the factory image on the slide. If you really look at what it is, perhaps from a slightly more robotics perspective, you take note of how it's pretty much just different joints, actuated joints, that are connected by links in a certain configuration, and they form a kinematic chain. This is an important perspective shift that will come back later in this webinar. Some of the common conceptions of the industrial robotic arm, where kind of robotic arms really came into mainstream discussion. And some of these conceptions aren't for those of you out there who are expert roboticists. These are conceptions about what some people just think. Those who don't know about robotics might say that the robotic arm is probably just large, heavy, and dangerous. It probably is often caged in factories, and there was a time when this was the case. They were really dangerous to be around. So even in this picture, as you can see, you needed to put cages around them as they're moving quickly and they're not carrying what's around them. With that, when you purchased a robotic arm, it used to come in a fixed configuration. So it was really a situation of you bought a fixed configuration and you got what you bought. You got that one arm and that's what you had. And the issue with that was that sometimes when you were done with its use case, it would just end up gathering dust on a shelf. And so robotic arms were often perceived to have, because it was one machine, it was a singular specified task for which you bought that robotic arm. They weren't also easy to program, so you often needed high levels of expertise to properly implement that robotic arm for whatever application you had it for. And they were really, really expensive, not just because of their first time purchase, but also to maintain, also to the running costs are just generally were higher. And these are some of the ways that people perceive robotic arms. And this is the definition that I want to challenge with you guys today. There are many types of robotic arms and that come in many different configurations. If we really look at it as the important point being the kinematic chain, you can go everywhere from an industrial articulated arm, as we've already looked at, to a SCARA arm, different configuration. A Cartesian or gantry system, which is, in most people's definitions, a robotic arm. Parallel delta arm, where the configuration changes from serial to parallel and changes kind of the entire dynamics of the system and how you have to program it. And then, even though this is very different from what we've looked at everything else, this is the most literal definition of the robotic arm, an anthropomorphic, human-like arm, which we often see in movies. These aren't the only definitions of robotic arms out there, but these are often some of the main ones that we think about. But the question here is, why do we have to limit ourselves in any way? If it really is a kinematic chain, what are the needs that we have in industry now for these robotic arms? Modern applications are coming up with a whole new set of needs. The same characteristics that we looked at that made robotic arms successful in the past are no longer necessarily what make them successful today. So to cycle through some modern applications, when we talk about mobile manipulation, we want to be able to put arms on mobile rovers, on legged robots, so that they can go out and they can manipulate the environment and take the arm out of the factory and into the real world, so to speak. We have applications where software has come a long way in, whether it's machine learning and AI, whether it's computer vision, whether it's autonomy. These are really useful in the digital world, and they have applications outside of robotics as well. But when it comes to applying them in robotics and using the power of that software to manipulate the real world, once again, we need robots that can be easily programmed and robots that can keep up with the rate of change of these fields. We need new approaches to pick and place. We have been using robots to pick something up and place it elsewhere in a factory for years, but we're discovering now that we can do much more with new types of grippers, soft robotics, and there's a whole field there that expands the use case of the robotic arm, and we need to be ready for that. We need arms that can move and be reconfigured to move with modern needs. We want them to be in commonplace environments. Commonplace environments are, we're starting to see robots out on the street. We want to take them out of their cage, quite literally, and put them in environments in the workplace, in research labs, where you can go and fist bump your robot and not get hurt in doing so. We want accessible actuation. Accessible actuation really is about making it more easy for the subject matter expert or for nearly the average individual who's out there to gain the benefits of robotics. You should not need to have a PhD in robotics just to be able to take the power of robotics and apply it to your field. And finally, inspection and maintenance. Now, this is a slightly more of a focused industrial touch, but I put this here because this is where we need to have increasing trust in our robots. When it comes to finding points of failure in different systems, we need to know that the arms we're putting out there are reliable, they are functional, and they're capable of interacting with the environment around them in a way that we can know we are getting the information we want. So pulling that back to the characteristics we defined earlier for how we've typically thought of robotic arms. They were large, heavy, and dangerous. Modern needs demand that they're smaller, lighter, and safer, so we can work in the workplace and we can put them on their mobile manipulators and so on and so forth. We need to take them out of their cage and we need to make them so that they can work with humans in environments that are more collaborative. We can get to the point where no longer do you have to buy an arm once and then be stuck with that arm. You can get to the point where I want you guys to all imagine a world where you can purchase a robot arm and then change its physical characteristics to better suit your needs after purchase. You've imagined it, and we're going to show you later today how that's possible. The singular specific tasks, no, arms can now do much more. They can be repurposed, they can be reprogrammed, and we can make it so that arms can do more than just that one given task before being put on a shelf. Not easy to program? We are at that point in robotics where we can make it accessible to non-robotics experts. If you are a biomedical engineer who is really more on the biomedical side than the mechanical or robotic side, but you still want an arm that can move things around in your lab, it should be possible to take a small, lightweight arm, putting all these things together, and put it in your lab. And at the end of the day, a factor that is often the driving cost is expense. And the overarching goal here is to be cheaper. And that doesn't just mean making hardware cheaper and the initial purchase cheaper. It talks about making it cheaper to develop better systems and making it cheaper to maintain these systems, to keeping the running costs low. There's a whole game here that needs to be played to make robotic arms cheaper, lighter, faster, and just easier to use. And so that's where I want to bring in what HEBI Robotics is doing. So HEBI Robotics' approach, as circled here, is design, build, and actuate. We have, over the last few years, supported major robotics development around the world in research labs and in industry. But specific to robotic arms, we're using the experience from out in that field to create, to better cater our tools, both on the hardware and software side, to making it so that we can have those reconfigurable robotic arms. We can have that modularity both on the hardware and software side. And we can make it collaborative. We can kind of hit all these objectives on fulfilling the needs of the modern robotic arm, taking it out of the cage and putting it into new applications into the workplace. And to show you, and the topic of this webinar really is redefining the robotic arm. But that comes down to redesigning how we approach the robotic arm. And to show you how HEBI is paving the way forward on that front, I'm going to pass it back to Willig, who's going to start answering the question of how are HEBI arms different and how are they ready for the modern day.
Thanks, Hardik. Yeah, so now you've learned about, what is a robotic arm, what defines a robotic arm, and where are we going, and how is HEBI making a difference. So as Hardik alluded to, these modern applications calls for this modern technology. So at its core, HEBI's technology is based around these modular actuators, these smart robotic building blocks. They provide, the flexibility to create a robotic arm system tailored to your specific task. On the right here, these red actuators, these X series actuators, are your more research-focused actuators that'll give you a wide variety of choices between speed, torque, gear train configurations, whereas the black actuators on the left are the R series actuators, which are more ruggedized. They're sealed to IP67, which is great for a dirty, wet environment, especially applications outside the lab, which is, as Hardik alluded to, kind of where a lot of these applications are headed. At the core, these actuators are series elastic. So what that means is you have your motor, your gearbox, and then there's actually a spring in series with that system. So what that allows you to do is it gives you built-in torque sensing. So you actually can sense torque feedbacks from these actuators, but you can also use the gear train to compensate for external forces like gravity and payloads. So it's a lot easier to interact with these arms and for the arms to interact with the environment. So you don't need safety cages. At the same time, this spring also can act as a shock absorber and protect the hardware itself. Next, there's also integrated encoders, IMUs with gyroscopes, accelerometers, and control electronics all built into these actuators. So you don't need external components to drive each of these motors. It's all built into these actuators. At the same time, you can do simultaneous control of position, velocity, and torque. And with that IMU, you know orientation. They're low power, which lends to the versatility and portability, which we'll talk about more. At the same time, they're using standard 100 megabit Ethernet communications. So it shows up on your Ethernet network, just like any other device with its own IP and MAC address. And then I'll talk about this in a little bit, but there are thoughtfully designed actuators with a through bore to make wiring very, very easy. So then looking at the ARM at a higher level, these actuators are building blocks, and they all come together with HEBI's accessory library of accessories, and they're all thoughtfully designed with that idea of the kinematic chain in mind. So at the base, we can really easily and quickly mount to things like T-slot extrusion or other interfaces, which allows us to have a breadth of different kinds of robots that you can mount to, whether it's mobile bases that HEBI designs, other companies' designs, or as Hardik mentioned, inspection and maintenance. You can put these arms in situ into some kind of area and have that arm mounted in place. We design brackets and accessories that you can put together. There's also 3D printed brackets, so that's further adding to the agile development of the platform. We have a catalog of parts, but if you can't find what you need, you can design your own, or you can work with us and we can expand our catalog, or we can help you design what you need. Some more topics here, like these links are designed with special holes, and the adapters have pins in them. So what you can do is the kinematics, which we'll talk about a little bit later, is all built into these actuators, and it's mechanically encoded so that the kinematics of the system goes and ties into the software. And then finally, you can attach whatever you need to the end of your arm and choose your own end effector. At the same time, there's multiple ways to integrate different kinds of end effectors, whether it's grippers, cameras, sensors, and since they're Ethernet-enabled devices, it's easy to adapt anything you need. And if necessary, we also have this I/O board that allows you to integrate other third-party sensors into our API. Like I mentioned before, the wiring is made very easy. There's a through bore with a multi-port switch for daisy chaining. So what you can do is you can literally take the wires and port them straight through the actuators, and the multi-port switch allows you to daisy chain from one actuator to the next. There's no need for service loops, so everything stays internal to the arm itself. In the X series specifically, there's power splitters that help with this daisy chaining, and you can even hide those inside the tubes. And then for the R series, power can be daisy chained through these terminal blocks, and you don't even need these power splitters, so the wiring itself is even cleaner. And then I'm going to set up this video. So what's really nice too about this modular system is we're minimizing the downtime for maintenance and repair. So as you see in this video, I'm doing a very simple teach repeat demo here where I'm giving the arm a set of waypoints and gripper commands. So I'm having it pick up this bottle of hand sanitizer, having it repeat that task multiple times. But then let's say, this runs for a few 100,000 hours, 100 or 1,000 hours, excuse me. And a certain actuator needs to be replaced or be repaired. It's within a matter of minutes. With all this generalized and standardized hardware, you'll see it takes mere minutes to unbolt an actuator, undo the wiring, switch out the actuator using all the same standardized hardware, put the actuator back in. And we have guides and assembly instructions on how to do this. And of course, we'll put videos like this online to help you do these kinds of swap outs. And then those waypoints are even saved. So I can start this code up again, and the arm is doing the exact same routine that I previously saved and had running before. So now we're up and running within mere minutes. It took me 8 minutes in this video to replace that elbow, whereas normally you would have to shut down your entire system, your entire assembly line, send the arm back, have a technician come in, repair it, and at the same time, we hope everybody stays safe and wash your hands. So where do we go from here, right? How do we get you started on building your own arm with HEBI tools? First off, we have pre-configured kits. So what you'll see playing here is a little GIF of the HEBI website, where you can find pricing, data sheets, assembly instructions, and other important documents about each kit on this web page. Bear in mind, since this is a modular system, what you can do is you can take one of these pre-configured kits and switch out. Maybe you need more payload. Maybe you need more payload, or you need to slightly alter these arms. You can go in and take one of these pre-configured kits as a starting point. Alternatively, we've created this tool called the 3D Configurator, which is an online build your own or configure your own HEBI arm tool, which allows you to build, test out, and then quote your own HEBI arm. So what I'm going to do right now is I'm going to switch screens and do a quick demo of what that looks like. So as you can see here, that I have my own arm kind of preloaded. So what you can do is this has HEBI's actuators, brackets, all built in to it. So if I wanted to, let's say, replace a bracket, it's got all our library of brackets and components built in. So you can go in here and start from scratch, or use an HRDF, which is something that Hardik will explain what that is a little bit later, to build your robot. Next, you can come to this test drive tab and get some technical specs about the reach, the payload, how much the arm itself is going to weigh, some power draw information, and you can kind of give your robotic arm a test drive. So you can move it around. And then once you find the right configuration for your task, you can buy your arm, or you can request a quote, right? You can send it to us and we can work with you to get this arm to you as quickly as possible. So now you've seen all the hardware that is the core of HEBI's technology. Now we're going to show you some use cases, some customers actually using HEBI arms out in the wild. So our arms are lightweight, portable, and easily integrated with other platforms. So here you'll see we've integrated with a ClearPath Jackal with a standard 6 degree of freedom arm and a gripper. And this is using ROS for any programmers out there. This code is all up on our GitHub. Next, a group at Carnegie Mellon University in the Robomechanics lab took our R-series actuators, built a 4 degree of freedom arm, and put it onto a different kind of mobile base that they procured themselves, and used it to be a mobile manipulator for their outdoor robot. Right here, it was scooping some dirt. They also have an auger on it. This is from the University of Washington, where they took a standard configuration, added an additional wrist to it. So it's a 7th degree of freedom with 4 wrists, and they're doing some motion capture with chopsticks. Next, here is our friend Julian from Carnegie Mellon University in the biorobotics lab, where he built his own configuration, taking actuators and components and completely configuring his own robotic backpack here, so that, you know, if you're out working, it's really nice not to hold pieces above your head while you're working, or hold on to scaffolding. And then there's, like I mentioned, there's a lot of different kinds of end effectors. So here we have a industrial customer who was working with pneumatic grippers, trying to have an automated bearing test system. So you can see it's just a very repetitive application here, but it shows the versatility of our arms being able to interact with 8 different kinds of end effectors. Here, the inspection and maintenance application comes into play. So we actually have a UT sensor at the end of this arm, and it's following pipe elbows. So the arms are very good at following complex geometries. This is kind of a different kind of configuration that you would normally see. And then lastly, we also love our interns. So this is a shout out to our intern from a couple of years back, Hans, who built a Delta style robot with HEBI actuators. So you can see the possibilities here are, you know, virtually endless. Whatever you can think of, you can do with these robotic systems. And now I'm going to pass things back to Hardik to talk about the ArmAPI.
Awesome. Thanks again, Willig. I hope everyone watching right now has had a chance to see where we're really pushing the boundaries of what a robotic arm means and what it can do, and how easy it is to build and put together, and how easy it is to integrate with other robots and put out in the field. My job now is to walk you guys through the software side of things. So if you have been watching our previous webinars as well, one or two of these concepts might be a little bit of repetition, but today's focus will be on the HEBI Arm API, and it will be fairly technical. So for the next 5 to 10 minutes, I'm going to walk you through how in just 10 minutes, you could get a new arm, you could plug it in, connect it to your network, and program a fairly sophisticated behavior and get up and running right away. So with that, let's get started with this technical dive. The first thing to talk about is our HEBI robot description format that Willig mentioned earlier. It is, in short, a versatile digital representation of your robot. It is a primarily XML format that has elements that help you define that kinematic chain that we talked about earlier in the webinar. So when you change your robot in the physical world, you should be able to just as easily change it in the software. The format stores robot configuration details and allows us to provide kinematic and dynamic information into our APIs. So on the left here, you'll see an example of what a 6 degree of freedom or 6-axis arm would look like in the HRDF format. That's the kinematic chain. You can construct that kinematic chain using all these elements that I have on the right, and you can pretty much construct any robotic arm that I challenge you to think of with these elements and put them in the kinematic chain. So it's really important to be able to explain to our software what the hardware we're working with is, and this provides a very easy format for us to quickly change. So if I was to, as Willig did in the video earlier, change the elbow, I could just go in here and I could update what my elbow has been changed to, and it would take a matter of maybe 30 seconds. The general idea behind the HEBI Arm API now is that normally when you have actuated joints and you have them put together with links, you are going to have something like you're going to be controlling each joint individually. And what this diagram is showing is that you're telling each actuator what to do on an individual basis. And from your central computer where you're doing all your logic, you might be able to put together more sophisticated algorithms and more sophisticated infrastructure for you to control that arm. Well, that's what we've done for you. So the HEBI Arm API is a system level API where you can now tell the entire arm what to do, and we'll take care of a lot of that additional logic that needs to go and is always there when you're working with an arm. So why have a special set of tools for arms? The mission statement for that Arm API, if you want to really know what the driving force is that we wanted to create a software infrastructure around a set of functions that make programming a robot arm of any configuration easier. So just as modular as our hardware is, just as configurable as our hardware is, we need the software to be the same. So to do that, we have provided high-level functions that simplify the code drastically. We clean up and reduce a lot of the code repetition. So when you're setting up for an arm, a lot of the same code that you would have had to write is now taken care of for you. So you can do the same thing that would have taken perhaps 20 lines in 2 lines. You can handle complicated math and physics and leave that actually to our API. So it can, like again, the math and the kinematic robotics math that needs to happen is standardized, and we can provide an entire API for that to make it really easy for you to get going. But for those robotics experts who are out there who really want to get access to the low-level control and some of the low-level details of the hardware, it's still accessible to you. So we do make it easier. We do provide this higher level abstraction. That does not, however, block away those lower level tools for you to use. we have four major, our primary four APIs are in MATLAB, ROS, Python, and C++. At the moment, the ARM API is in the process of being released for all of them, and it is particularly stable right now in Python and MATLAB, closely followed by a upcoming C++ release. With ROS, there's a little bit more nuance there because ROS has certain similar tools, but you can choose to work with theirs, you can choose to work with ours, or you can choose to work in Python or C++ inside ROS. We were able to cater to all these different types of users and choice of how you want to use it. So with that, let's start looking at what the basic outline for controlling your arm would be. We want it to come down to the bare bones skeleton for what it takes to control a robot arm in code. And the priorities here were to make it easy to use. It should be possible to get up and running quite quickly, and it should be easy to modify. As I mentioned before, when you change the hardware, the software should change as easily as possible with it. Some of the code that I'll be going through right now, all of the code I'll be going through right now is actually available in our GitHub repositories, github.com/HEBI Robotics. So if you want to take a closer look at the expanded code files, I recommend you check out this link, bookmark this link, and keep it as the most useful resource you can have for HEBI software. When you are writing the code, the three main things that you want to be doing is you want to be able to create the ARM object. You want to be able to add any plugins and integrations so that you can work with the other tools that are out there. And then you want to be able to have a kind of central control loop where everything is basically where the fun meat is taking place. This is not a limiting factor. You don't have to work with these three sections, but in most cases, this is the skeleton that you're going to start with before you add more meat. Let's talk about creating the ARM object. So when I have an arm, and I'll show you later today with a real live arm what it takes. I have a physical arm and I have described it in my HRDF. The actuator names and family that I talk about are what show up on my network. So when I've connected my arm to the network, I should be able to see it pop up in HEBI scope. If you watch our previous webinars, you will know what scope is. In brief, it is a custom debugging and monitoring software that is available on all your platforms. I won't go into it too much today, but in short, for all you need to know today is that it allows you to see the actuators that are on your network and work with them and debug them when necessary. So here in scope, once you've seen your actuators pop up on your side, you can see that the family is ARM and the names are all these different actuator joint names. With that, if you've described it in your HRDF, between these two sources of information, we can create a comprehensive ARM object in your code that has all the kinematic information, has all the information on how to connect with your arm, and is really just ready and set up for you to go. So it makes it really quick. It's pretty much just 2 lines of code that we'll look at right now to get going. Once again, we have not limited that, however. So if you do want to provide additional important information for creating your arm, anything from gains files to improve your control gains and performance, to different types of end effectors, set small parameters like command lifetime or command frequency, or provide a virtual robot model, which is similar to the HRDF. All of this is supported with the ARM API. So you can work on the simple side of life, or if you really want to get more specific, that is all supported as well. As I promised you guys the technical dive, this is where we're going to look at small snippets of code. This is done in Python, and I will reiterate that it is supported in MATLAB, C++, and through our other APIs, ROS as well. But Python is a common language that I'm going to choose to pursue to use to explain some of these concepts. So in the lines here, all I've done in my code is show that the ARM family that I'm looking for, as we saw in the scope screenshot earlier, is ARM. I have all my module names, and this is a 6th degree of freedom arm that we're working with. And I provided the HRDF file that describes the kinematic chain. All I have to do there is in a single line, create the ARM object, and it's going to have, as I mentioned earlier, all the important information captured in that object and created within, what is this, 4 lines of code. Now that we've actually created the ARM, we are going to then look at what plugins and integrations we might want to add. So some of the most common ones, or what I'll cover today in the interest of time, is, so if you have an end effector, how do you want to add your end effector onto your arm? I'm going to show today what it looks like when you add the standard HEBI grippers. So the grippers come with they attach to the last actuator in your arm, and they come with an additional actuator called the gripper spool that helps the gripper, that actuates the gripper to open and close. When you're working with this actuator, once again, looking at some code, the process is very much the same. You have to find the family and name so you can locate it on the network, and then you have to provide the parameters of what the open effort and close effort, or the torque required to open the gripper and close the gripper that you'd like to use, and that can be changed depending on your gripper. In this case, we were using a special gripper class. You'll notice here arm.API.gripper, but you can comfortably adapt your own external grippers, whether they're from whether they're 3D printed by yourself or you have purchased it from another company. They're all able to be integrated in using this setup that we have, and it's as simple as doing it as adding it as a set end effector into your arm. We'll talk later about how once you've added to your arm object, it will automatically continue to update in the background and simplify the process of interacting with external hardware. What I'll say here also is that this end effector isn't limited to grippers. It can also be, it could be a camera where you're getting input. It could be really anything you can think of that you want to attach to your arm, any piece of hardware. With that, we also provide, looking at some more of like the plugins, we have, if you want to add something like a gas spring, or you want, so basically you want to change the dynamics of your arm in the real world, you can add simple plugins that, such as that for a gas spring, that change how you control your arm. And the way to look at another plugin is actually to look at what we, it's the same behavior as with different types of controllers. So if you're a roboticist, you might know about impedance control, or impedance control is, in brief, it is when you create virtual forces in the 3D Cartesian world for your arm. So at the end effector, if I am creating impedance in one direction, if I push in that specific direction, it will push back at me. So even doing sophisticated control mechanisms like that can be as simple as, in this case, we have our custom HEBI impedance controller inbuilt into the ArmAPI. So you can get up and running again, once again, by just loading the impedance controller, adding it as a plugin, and then from there, setting the parameters for your for that control. So you feel free to pause this video or this recording afterwards if you're watching this to take a look and note down some of the ways in which we've reduced multiple lines of code into singular functions. And finally, the fun stuff. So the main control loop is where all your kind of main functionality is going to get added. So now that you've connected to your arm and you've fed the software the relevant information, you've connected any additional hardware and any plugins that you need for your arm, this is where you start making the arm, in colloquial terms, do things. So the most important function and your biggest friend is going to be arm.update. What this does is it really, in a sense, refreshes the entire arm object. It receives the feedback from the modules, it computes the pending commands that need to be sent next, and it updates the state of any integrations or plugins that you have associated with the arm. So that's why we make it easy. That's how we make it easy to add plugins. You don't need to be handling those necessarily separately. We'll just continuously, comfortably integrate it into our main control loop. With arm.update, the other important function is arm.send. So once you've refreshed your arm, so to speak, you want to be able to change some commands and then send those updated commands out to the arm so that from now on, at each refresh, at each update call, you are sending those new commands. So again, relatively simple function, but between these two, you're able to create, again, the bare bones code that we have. So if you're running a main simple while control loop, once again in Python, the abort flag can be whatever you choose, but all you need to do is update or refresh your arm at the beginning of each loop and send any updated commands at the end of that loop. And in the middle, between those two, you can add whatever logic you need to control your arm. Once again, I will reiterate that this was made to make it simple. It takes care of a lot of the considerations you have to do when talking about your arm and worrying about it in the software simply in these two functions alone. And we're going to look at how that ties in with making your arm move, which is the next point. Arm.setGoal. In the next slide, I'll explain what a goal is, but a goal is, once again, using as simple terms as I can, and to simplify my explanation of this, the goal is your description for how the arm, of where the arm needs to go. So it's the target, it's the desired waypoints, it's basically the goal that you're trying to achieve. So the two functions here are simply the set goal and cancel goal. The goal is your target in motion, as I just mentioned, and so it's the set of waypoints you want to go through. And so when we create a goal, we provide inputs that you want to work with. So the typical inputs you might want to provide are positions. So a waypoint is simply a position for the arm to hold at. So if I set one waypoint and then I set another waypoint, I'll have two sets of position values. If I want it to flow through the waypoint or like continue moving through the waypoint, I can send some velocities. I can provide accelerations. Aux states are what we use to command plugins or end effectors, and you can read more about that in our documentation. But the goal is a way to collect all those inputs, feed them into this goal object, and then pass it to the arm. And when the arm receives that goal, it is able to take all those inputs and calculate smoothed out trajectories for the arm to follow. And that's what we're going to see in our live demonstration in a second. The goal is really useful for collecting that information that you need to tell your arm where to go, how to go, and when to go. So here we have we create a goal from the ArmAPI. We then describe a waypoint, which is just, we're going to go to all the 0 positions for each of the 6 actuators that we have in our 6 degree of freedom arm. We're going to add that as a waypoint. So we're going to tell the arm, we're going to say that this is your goal, and we're going to say t equals 3, which means that I want you to take 3 seconds to go to this position. From there, all you have to do is arm.set goal. You can construct your goal however you want. You can have multiple waypoints. You can have different positions. You can have different types of waypoints. And so where I create this waypoint here, I've only provided time and position, but you really, as I mentioned, can provide a whole plethora of inputs beyond just that. So taking this code that we just looked at for creating and setting a goal, you want to add it to your main control logic, and lo and behold, you'll have a fully, and with a few more lines of code, so maybe setting a few more waypoints, setting different behaviors, that's going to be your code. Just in this simple creating an ARM object, adding a plugin and integration, and then having the simple control loop, you can already be programming your arm to do sophisticated maneuvers. And I've spoken about this enough, so let's take a look at what that looks like in action. A reminder here that as I'm loading up this demo, we are open to questions. So if you have any questions about what I've just shown you or what Willig has shown you, please put them in the question chat.
Yeah, we actually have a couple of good questions here. We've got one from Felix who asks, what is the maximum payload that can be handled?
Yeah, so that's a good question, Felix. Thanks for asking it. So it totally depends is kind of easy answer out of it, but I'll dive a little bit deeper into that. It depends on your configuration, right? The other easy answer is our most common pre-configured kit is something like a 6 degree of freedom arm that I showed earlier, and that's maybe about 1 kilogram of payload. But at the same time, these arms are totally reconfigurable, so you can totally work around and get different kinds of payloads depending on what your application calls for, right? So we have different ways to increase your payload by doing things like doubling up shoulders, which you can find more information about online. You can add gas springs, like Hardik mentioned, that helps offset some of the payload and work that the actuators have to do. The only downside to adding gas springs is it limits your workspace. So there's a lot of different ways you can go about getting more payload, but there are, sometimes sacrifices you have to make to get that higher payload. Yeah, I think that answers the question. You got anything else as Hardik gets set up?
Yeah, we have one more that might be relevant to actually what Hardik's working on. Barbara asks, do you expose the ArmAPI outside of a hardware purchase?
Yep. The ArmAPI is actually, if you go to our GitHub right now, if you were to go to our documentation and find the download links for our, for example, in this case, the Python API that we have, I'll talk to the camera actually, you should be able to find the ArmAPI and use it with use it for your various applications. feel free to put in a little bit more in your question as to what particularly you're thinking, and I can give a more specific answer. But in short, yes, I'll say that. Before we get to any questions, though, I will run these demos in the interest of time. So what I have here is, hi again. So I have a whole setup next to my computer here. So you're seeing the behind the scenes here. But what I'm running right now with the ARM is I'm running what we call gravity compensation. So if you remember that loop that we spoke about, that control loop where all you have to do is update and send, that's all I'm commanding right now. What that means is that the ARM object that was fed just the bare bones information of the actuator names on the network and then the HRDF from there, it knows what torques it needs to command at each level to support its own weight and gravity and make it feel like it's basically weightless as I'm moving it around. So this is kind of demonstrating how we're taking care, again, once more, of all those background things that you sometimes might need to think about. This ARM is a little bit like, I'm strong, but I'm not that strong that I can just move it around like this. And the additional effort that the ARM is providing me makes it highly more collaborative than it would have been otherwise. Let's look at a slightly more fun demo now. So if I load up from the elbow change video, you saw us do a teach repeat demo. I'm going to do the same thing. I'm going to talk through a little bit more of the technical aspects as well. So what I have here is an iPad running HEBI Mobile IO, if the camera would like to focus. So the HEBI Mobile IO is a simple way, it's an app on the App Store and the Android Store that you can download, and you can use it to provide input to your robotic system. So what I'm going to do now is I'm going to run the teach repeat example, and I'm actually going to use the same props that Willig did, if I can find it. Oh, I can't find it. Oh, well. I kept it further away. So this is the hand sanitizer. What you want to be doing is making sure that, I'm just going to run it again. There it is. So we start in that same gravity compensation mode where the arm is supporting its own weight. I have my object here. So what I'm going to do is I'm going to use the buttons on my iPad to train the arm. So let's set a initial waypoint here. Let's have it pick up from roughly this corner. So I can come here, and then I'm going to move in closer. Once I pick it up, and I can freely move around the arm as I want. It's tracking all the relevant information. I can come over here, and I can put the arm down, and then I can make sure I move up, and I've just trained my arm. That's kind of all it took. From here, I'm going to start playback. Whoops. But yeah, I have the hand sanitizer. I can take it out, wipe it. And so the thing I want to highlight here is that all this was basically an expanded version of what I showed you earlier about putting some logic in the main control loop. So this is a demo that you can find once again on our GitHub called Teach Repeat, and it shows how the inputs I'm providing are simply the button presses, and with those button presses, it is creating goals or expanding the goal that we created. So it's adding waypoints to that goal. And then at the end of that, when I click the play button, it just sends that goal to the arm saying, go move. Once again, the infrastructure is all there for you to be quick and easy about it. And finally, the fun example that I'll show you, and if you have been watching our YouTube channels, which I highly recommend you do, you will find that you might have seen a similar demo, and that is the AR kit demo. So an AR kit, the AR kit that comes on the iPad allows us to pretty much control using the accelerometer and IMU in the iPad to control how the arm is moving. Keep sending in those questions as I'm just barraging you guys with information. So here, now that I've turned it on, as I move the iPad up, the end effector will follow. I think I'm experiencing some slight network delays, but there, smooth again. So I can come up to the camera and I can go, hello, all with the input of my arm. So again, this is just changing around the same infrastructure, it's changing the inputs that we take. So now we're taking IMU and accelerometer data from the iPad, and we're once again working around that same main control loop. So these are really quick demos. Once again, they're quick because of time, and we'd love to keep you forever on this webinar. But please ask any questions about how this works or how you can learn more about this, because the one last thing I'll add there is that this code is not limited to this configuration. You can change the configuration, and with 1 or 2 changes of code, 1 or 2 line changes in the code, you could be running the exact same code and get up and running really quickly. So with that, I'm going to pass it back to, oh, sorry, I'm going to wrap up on the software side. So I'm going to have the presentation back up in a second. So real quick, just to put it all together, with the software side of the HEBI ArmAPI, there are many, many more functions and tools to help you with your development. So we have tools, especially for the roboticists out there. You will appreciate the support we have with the forward kinematics and inverse kinematic functions. We can set joint limits. We can set different types of constraints. We can set the arm to actually turn off when it collides with something, really aiding to that collaborative aspect. And we can do a lot more. So I encourage you to explore that. In brief, we're trying to do in 100 lines what used to take 400 lines. So reduce drastically the amount of code that you need to write to get up and running with a robot arm. We want you to be able to confidently add or change hardware and then adapt the software in seconds. And that's what the ArmAPI is all about. A reminder, though we have moved a series of a lot of the code under the hood, it's not completely inaccessible to you. So if you do need to change that, and if you do need to get that low-level control, you can. And finally, again, you can change the type of input, whether it's an iPad, whether it's different sensors, it's a LiDAR, it's a camera. All those things are supported with the same plugin infrastructure, same end effector infrastructure in the ArmAPI. So we encourage you to think broader and think about how. The one other thing I'll mention is if you're doing machine learning or AI applications, you can also plug right into using the plugin system and get all the joint level information to better understand how an arm works, or really get nitty gritty about how you want to improve the performance of the arm. The possibilities are really, really, for all practical purposes, endless. And with that, I'm going to pass it back to Willig to talk a little bit about what the HEBI community is all about and how you can work together with this as we wrap up.
And while Willig gets ready here, I have one quick question from Soham about the API for Hardik. It says, can the API be customized to integrate 2 6-DoF arms working on a single task?
Yep, for sure. In the same, again, I showed you the very simplest version of the API, so a main control loop, but you can comfortably set up 2 arm objects where you're controlling different arms. In fact, I encourage you, again, to check out our YouTube channel where we have videos of multiple arms being run from the same code. And so, yeah, you can definitely integrate 2 6-degree of freedom arms to work on the same task using the ArmAPI.
Great. I know we have a lot of questions that came in, so Colleen, if you want to ask 1 or 2 more before we move forward, we can take those now.
That sounds great. Okay, so I've got one here from Ben. He asks, using the example of a robot performing the UT scan, is it possible to control the amount of force that the robot applies? Is the force applied at the end effector controllable? Does the force limiting need to be set up on each joint individually?
Yeah, so that's a great question, Ben. Absolutely. The answer is yes, you can control force. Since these are series elastic actuators, we can do it at the actuator level, but also at the arm level. One way to do that is through impedance control, which is what Hardik alluded to in one of the earlier slides. So what you can do is you can just say, at the arm level, I want this amount of force applied over my, once you create that surface, you can have the arm end effector make sure it's always applying some kind of force. The short answer, yes. So we'll move on with the presentation, and we'll take some more questions after. So with everything we've said today, the hardware, the software, robotic arms, HEBI, we want to all of our customers and all the engineers and everybody that works at HEBI, we have a community here, and we want all of our customers to be able to take full advantage of the platform and all of these great things that we have to offer. One way to do that is our wealth of documentation, right? So we have this website called docs.hebi.us, and that's really what sets us apart is our documentation. So you can go on and you can find quick start guides, core concepts, background information, all this mechanical information that I went through, a lot of the software walkthroughs that Hardik talked about. You can find downloads, whether it's mechanical drawings or links to other types of documentation that you need. But at the same time, you can find CAD files at cad.hebi.us. A lot of our demos and even a lot of the videos we showed today will be up on YouTube, on our YouTube channel. And then a lot of the code that Hardik showed today and a lot of our demos that you've seen prior will be on our GitHub. And those are all public repos. At the same time, support is always at your fingertips with HEBI Robotics. In the past, you could send us emails and we're very responsive, but we really want to push this HEBI community forum. We want everybody to go create accounts. It's regularly monitored by our engineers, and you can even collaborate with other HEBI users if you have a problem and someone else is working on something very similar to you. That's maybe not one of us, but a customer or a user out there that maybe they've encountered something very similar and they've already solved it. Go find it on the forum, and also go share your success stories on there too. If you want one-on-one assistance, like I said, you can always email us or submit a ticket online. And lastly, we want you to join this community so you can stay in the loop by joining our newsletter and check out the past webinars that I talked about earlier with the generic overview and introduction to the HEBI platform as a whole. And then also you can learn about our new maps technology with inspection and maintenance.
And so to put some final touches on today's webinar, we're going to talk about what we hope to leave you with today. The most important thing is that robotic arms and their applications are changing. We took some time to change how we perceive the robotic arm, how we recognize that the needs of the modern day are different from the needs when robotic arms were first created in primarily factory-like and industrial spaces. And we recognize that we need new hardware and software tools to match all of the world's new demands. As the world moves towards more collaborative and more sophisticated applications of robotics, we need to be able to match that with our tools. HEBI Robotics is really paving the way forward with modular, reconfigurable, and collaborative hardware. We want to make it easy to use. We want to make it accessible to more people, to more industries, and as well as that, just simply more use cases. Robotics is powerful, and we want to see it taking effect in more places than it is right now. And the software tools are designed to move you as fast as the hardware, and that's challenging because the hardware is really easy to change, and it's really easy to get the system that you need. And with these tools, we want to open doors for roboticists and subject matter experts everywhere. Cannot reiterate that it's designed so that it's not just the PhD in robotics who is working with these tools and creating useful robotic solutions. It is the subject matter expert. It is that person who may never have looked at a robot before, but is now realizing that they can use a robot in their application. Putting this all together, this is just one way in which we accelerate the future of robotics. Our tools exist outside of the spectrum of robotic arms as well, and I encourage you to check out our past webinars or any of the resources that Willig mentioned earlier to find out the other ways in which we are changing the game. And I definitely encourage you to check out HEBIRobotics.com and ask any further questions as we wrap up this webinar. So thank you everyone for your time, and please reach out if you have any questions. I'm going to let Colleen take over from here and answer your questions.
Yeah, we have some great questions here. The next one that we have is from Ben again. He says, with the actuators having a spring in line, I would expect that this would negatively affect the positional accuracy and repeatability. Can you please comment on the positional accuracy and repeatability?
Yep, I can take that one. Since these are series elastic actuators, what we actually do is we encode the deflection of that spring. So we have a very, very high resolution encoder that's before that spring and after that spring. So we know the positional accuracy of the output even with that spring, but also that we can sense the deflection of that spring, which gives us that force sensing. So we do have that encoder on the output directly after the spring. That gives us that resolution.
And to expand on that just a little bit more is that returning once to what the new modern application requires, you don't always need an arm that can be super precise. Sometimes the ability, and oftentimes the ability to be compliant with the world around you is just as valuable and takes away that need for minuscule precision. And that's where we really thrive.
Excellent. We have another great question here from Stefan. He asks, very cool modular builds you have. Thanks. I can see how this is very useful for prototypes and research. You also say you target industrial applications. How do you handle the regulative demands in this area? For example, that you have to guarantee the reliability of safety functions.
Yeah, so there's a lot of different ways you can do that. On the mechanical side, what you can do is we have built-in M-stop, right, emergency stops. So what you can do is you can hard stop electrically in the wiring. You can add e-stop buttons, things like that. In the software side, we can even send and set safety limits. And Hardik, I don't know if you want to expand on that.
Yeah, I think you can do a lot on the software side as well to make sure that we can meet the limit, the regulative demands that are required, or especially the reliability and safety of the functions. And because we can move quickly, we can also test these quickly, we can prototype quickly, and we can make sure that we get the system configured and purposed exactly as is required. But in that, actually, I'll expand on that a little bit and say that in general, this is a pretty tough question to answer when it comes to like, how do we handle the regulative demands of like the industrial space? We are moving into industrial applications, but we recognize that the requirements might be different per industry or even per application. So we're handling things on a case-by-case basis right now. So as we approach a different industry, we also expand our technology accordingly to make sure that we are meeting those regulative demands. So if you have anything in specific, again, please reach out, if not by question here, by email, and we can explain more how we do that on the industrial side.
Great, and I've got one more here that I think would be good to share. This is from Camilla. She says, can your arm work faster than a UR arm?
Okay.
Yeah.
Oh, sorry, you go.
Yeah, sorry. It's a hard question to answer, but for certain applications, sure. It's the real power of the HEBI platform is the customization, but it's really not comparing. You're not comparing apples to apples, right? They're not really the same thing. We deliberately are not competing with UR or other industrial systems head on, which makes us so unique. If that answers, Hardik, I don't know if you want to add on anything to that.
No, I think it's important to realize that we're not like the perfect hardware, but we bring a lot to the table that's different and opens up doors for applications that are different from what the UR is most capable for. And we encourage you to think about new applications because we can customize, we can repurpose a lot faster in many cases. And we're customized, we adapt.
And kind of going off of that, kind of a last question here is, what is your target market? Is it only for lab work?
The target market is broad. The origins of HEBI Robotics came out of research, and so we are fans of the research lab, but that doesn't mean that that's our only target audience. So the tools are really powerful for the researcher, but they're also really powerful for developing new and novel industrial solutions. So what you'll find is that the people we work with aren't just those who want to discover the latest new and fastest robotics algorithm, but it's also those who want to see robotics out in the field, in industry, or even in the workplace. So our target audience is really broad, and we find that our tools allow us to cater to many different audiences.
You think we've got time for one more, folks? Yeah, so this comes in from Stefan. He is following up on a question he asked previously. He said, specifically, I wonder whether you have performance level rated safety functions, for example, the emergency stop we mentioned. For his application, they require this according to the ISO 13849 standard.
Yeah, so you know, like Hardik said, it's application dependent. I'm not familiar with that specific standard. I'd have to do some research to see what exactly that calls for. Send us an email, either at info@hebirobotics.com or engineering@hebirobotics.com, and we can follow up with you about your specific application and need.
All right, I think that is all we've got in for questions at the moment. Thank you guys for joining us today. Hardik and Willig, do you have any last thoughts before we head out?
In case this wasn't too obvious, Willig and I are extremely passionate about what we do here, and so is the rest of the HEBI Robotics team. So if you have any doubts or any applications that you may think are possible or even not possible, we appreciate the email, and we're always happy to talk and discuss how we can change the boundaries of what is possible. We're not just trying to make what is out there faster. We're trying to do new things and find new applications where, as our slogan goes, we accelerate the future of robotics. So thanks everyone for your time, and from our end, or at least from my end, please, we love to talk robotics, so don't hesitate to reach out at all.